We've been discussing the approach to trigonometry using right triangles, and those definitions would give us the trigonometric functions of an acute angle in a right triangle. Now let's generalize our definition to encompass not only acute angles but also angles that are not acute. Here's our definition. The situation we have is an angle in standard position, which means the vertex is 0, 0, and the initial side of the angle lies on the positive x-axis. The terminal side of the angle is wherever you need to measure to, okay, in order to describe your angle. And we have a point on the terminal side of the angle that we have labeled the point as the point P, x comma y. Okay, so that's an important ingredient, that we know a point on the terminal side of the angle. Okay, and in this context, what we learned about right triangles would still hold true, because this is the rectangular coordinate plane. We can see the natural right triangle that's formed here. And we can also see from 0, 0, we go over x units and we go up y units. We form the legs of the triangle, and then the value r in the figure would be the distance between the origin and the point x comma y, which corresponds in this particular case to the hypotenuse of the right triangle. Okay, but in general the length r is the distance from the origin, so from the vertex, to the point on the terminal side. And for that reason, r will always be described as the square root of x squared plus y squared, okay? Because again, it's the distance between the points 0, 0 and x comma y. Okay, now our definitions will be phrased in this manner. The sine of the angle theta will be the y coordinate of this point divided by the length we call r. That is consistent with our right triangle definition if a right triangle is what we're looking at, okay? Cosine will be defined as the x coordinate over r, as you can see here, okay? And that is still consistent in this right triangle world with the side adjacent theta divided by the hypotenuse. Okay, but what changes is if the angle is bigger than 90 degrees, the position of the point x comma y will become very important. Okay, so it's natural for us to define tangent as y over x, and then it's consistent with opposite over adjacent. Cosecant is naturally the reciprocal of sine, secant the reciprocal of cosine, and cotangent the reciprocal of tangent. Also, while we're here on this definition, let's talk domain values. If you're in this world where you have a point xy on the terminal side of your angle and a value r that's the distance between the vertex and the point P, then it is important to note that r is always positive. Okay, so r itself is never 0, it's never negative. And that x and y, however, can be anything except the vertex point. So x and y can be anything except them both being 0. Alright, for that reason, the domain of the sine function, if you look at the definition y divided by r, you're never dividing by 0. Y is always defined as a real number. So the domain of sine of theta is all reals. Okay? Now I need to clarify that a little bit more. All real what? All real values of theta. Okay, now let's clarify that even further. Theta is an angle. If you're talking about the real number values of theta, you're measuring theta in radians. If you were talking about theta measured in degrees, you would say the domain is the set of all possible degree values of theta. Okay? In other words, the sine function is never undefined. The same thing is true of the cosine function. But the other guys, tangent, cosecant, secant, and cotangent, all have either an x or a y in the denominator, and I want you to notice the commentary here. Tangent would not exist if you divided by 0. Ditto for cosecant, secant, and cotangent. So I want you to keep in mind that if any of those values were 0, then those four functions would be undefined somewhere, okay? Each of them, I mean, in different places. So let's talk about those places in just a moment. All right, so let me go back over this. We have a point on the terminal side of an angle. The angle's in standard position. And what's going to be critical is that we identify a point, and then we can calculate the distance between that point and 0, 0 to get r. Okay, keeping that in mind, let's put our special triangles in context with this situation. Okay, I'll just do one of these two angles. I'll do the 60-degree angle here. All right, pretend like this is 60 degrees. It's not to scale. But if it were, the other angle, the complement, would be 30 degrees. And in my 30, 60, 90 right triangle that we derived in the earlier lesson, we see that whatever we choose the hypotenuse to be of the triangle, the side adjacent 60 is exactly half of that value, and the Pythagorean theorem gives us the third side. So notice that if I place that special triangle and I place 60 degrees in standard position, the point that I generate is 1, root 3, and my r value is 2. So if I apply, let's just try the sine definition, the new one we have is y over r, then I would faithfully say y coordinate divided by the value of r and have my calculation. But yes, when you see a right triangle, that's consistent anytime you see a right triangle with our right triangle definitions. Okay? All right, likewise, we could place the 45, 45, 90 right triangle in standard position. This one actually looks more correct. And if I do, I like to use the two legs to be 1. Whatever you choose, they have to be the same. And then I use the Pythagorean theorem to calculate the third side. So in this world, our ordered pair P is 1, 1, and the distance between P and the origin is the square root of 2. So let's try cosine this time. Cosine of, and this would be 45 degrees, my apologies, I meant to write that in, of 45 degrees, by definition, has to follow as the x coordinate divided by the length r, and the x coordinate is 1 and the length r is root 2. Okay, and again, that's consistent with adjacent over hypotenuse when you see a triangle. Now let me back up over here. Actually, let me write this in the same kind of manner. Okay, because we were doing 60 degrees over here. Okay, so that's how the true definition works, and we'll keep practicing that in the next examples.